everyone, thanks so much for joining me for this video. Today we're going to be learning about intermolecular forces, and these are the learning objectives. So the first is to learn about intermolecular forces based on permanent dipole-dipole interactions and induced dipole-dipole interactions. And then we're going to look at a bit about hydrogen bonding, and then explaining the properties of water resulting from hydrogen bonding, so the density of ice, and also relatively high melting and boiling points. Then we'll explain the solid structures of simple molecular lattices, so covalently bonded molecules attracted by intermolecular forces. And then we're going to explain the effect of structure and bonding on the physical properties of covalent compounds with simple molecular lattice structures, including melting and boiling points, solubility, and electrical conductivity. So there's three types of intermolecular forces that we need to know about. The first one is van der Waals. And this is the weakest type of intermolecular force, and this is because temporary induced dipole-dipole attraction is created due to uneven electron distribution, and this is because of the movement of electrons. This occurs even in molecules with no polar bonds, so this is actually present in all simple molecules, so all covalently bonded structures which are simple molecular. And the rule is the bigger the molecule, the more electrons it has, so the greater the van der Waals forces. So for example, if we had chlorine, so we already have a chlorine here, and the electrons are spaced evenly because there's no difference in electronegativity because it's not a polar bond. If we then approach another Cl-Cl bond, which has even distribution electrons again. So what would happen is that when it approaches, we have this Cl-Cl here, and another Cl-Cl here. These electrons over here get repulsed. So more electrons gather around the chlorine which is further away. So then this chlorine becomes delta negative and this becomes delta positive. And because of that, more electrons gather around this chlorine because this is delta positive. So then most of the electrons are attracted to it. So then they do this. So more electrons are attracted to this delta positive, so less are attracted to this chlorine. So what happens is that this then becomes a delta positive, and this one becomes a delta negative. The second intermolecular force is a permanent dipole-dipole attraction, and this is found in molecules with polar bonds because they have an overall dipole. A dipole is just a difference in the electronegativity, basically, and there are attractions between these permanent dipoles in neighboring molecules. So, for example, if we had hydrogen chloride, and then we had another hydrogen chloride. Chlorine is a lot more electronegative than hydrogen, so that would get the partially negative charge, and the hydrogen would be partially positive. Same with this one. And so there would be a permanent dipole attraction between them because a partially negative charge will be attracted to a partially positive charge. And if they're not arranged in this way, they normally rotate in order to be attracted like this. So the third intermolecular force you need to know is hydrogen bonding. And this only occurs when a hydrogen atom is bonded to a very electronegative atom. So normally only fluorine, oxygen, or nitrogen. The electronegative atom needs to have a lone pair available to bond with the hydrogen atom of another. And the polar bond leaves the hydrogen nucleus exposed, and so there is a strong attraction from the lone pair on the fluorine, oxygen, or nitrogen of one molecule to the exposed hydrogen nucleus of another molecule. And if we have a look at water, for example, water looks like this. And there's two lone pairs. The oxygen will be the partially negative, and these two will be partially positives. And then these will actually form bonds with the hydrogen of another water because this is a lone pair. So this forms with water, another water, and then it happens again because the oxygen will always be partially negative and the hydrogens will always be partially positive. So they'll always be attracted to the oxygens of another water molecule. And one thing to note is that this angle here has to be 180 degrees. So a straight line. So the importance of hydrogen bonding, for example, the molecules in ice are slightly less packed than in liquid water, so they form on top of ponds, and this insulates the ponds, so it basically keeps the fish alive. So that's quite a good feature for it to have. What happens when ice forms water is that the hydrogen bonds break. So hydrogen bonds are actually the strongest out of the three intermolecular forces, but it's a lot weaker than covalent bonds, so they don't take very much energy to overcome really. So they can break to form water, but they can be really easily reformed to form ice. And the reason why I drew the waters to be 180 degrees is that a rule for hydrogen bonding is that always when something hydrogen bonds, the angle will always be 180 degrees. This is just a general rule, but simple molecules have low melting and boiling points, and giant covalent structures have high melting and boiling points. And this is because with simple molecules, we're trying to break the weaker van der Waals forces or whatever intermolecular forces there are in between the molecules, compared to in a giant covalent structure when we're trying to break the strong covalent bonds between the atoms, and that takes a lot more energy to overcome, hence why it has a higher melting and boiling point. Now we're going to talk about hydrogen bonding in water in more depth. So there's two features of water that are caused by hydrogen bonding, and the first being that ice is less dense than water, and the second is that water has a relatively high melting and boiling point. So firstly, ice is an open lattice with hydrogen bonds which holds the water molecules apart, and so when it melts, the rigid hydrogen bonds collapse, and this allows the water molecules to move closer together. The distance the molecules are held apart is what makes ice less dense than water, because water molecules are so much more closer together. And secondly, hydrogen bonds are much stronger than van der Waals forces, because hydrogen bonds are the strongest out of the three intermolecular forces. And so this means that more energy is needed to break these hydrogen bonds, so they have a higher melting and boiling point compared to different molecules, even though water is also a molecule. So now we're going to move on to some questions. The first question asks to place the following elements in order of strength of the van der Waals forces between the atoms, weakest first. So we learned before that if you have bigger atoms, that means more electrons. So strength of van der Waals increases. And so basically we just need to place them in order of size. So we have argon, which is in group 0, helium, which is also in group 0, krypton, which is in group 0, and neon is also in group 0. So that doesn't help us. So we look at the periods. So argon is in period 3. Helium is in period 1. Krypton is in period 4. And neon is in period 2. And so now this helps us a lot because we know that helium has 1 outer shell. And we know that argon has 3 outer shells. 3 shells, sorry. So we can tell that krypton is the biggest atom because it has 4 shells. And so the order of the elements in strength of van der Waals forces would be helium, neon, argon, and then krypton. So this would be getting stronger. For number 2, draw 2 hydrogen bromide molecules to show how they would be attracted together by dipole-dipole forces. So if we draw 1 hydrogen bromide, we can see that bromine is in group 7 of the periodic table, so it's a lot more electronegative than hydrogen. So we give that the partially negative charge and hydrogen the partially positive charge. And so if we had another hydrogen bromide molecule here, which had the same thing, then this partially positive charge would be attracted to this partially positive charge. And so we would get a permanent dipole-dipole attraction between these 2 hydrogen bromide molecules. And what I was saying before was that if, for example, we had hydrogen bromide like this, but one of the hydrogen bromides was like this, and these were delta negative, delta positive, then this one would rotate in order to make this configuration so that they would be attracted to each other. Hi everyone, thanks so much for joining this video. We're going to look at some harder questions for the topic of intermolecular forces. So the first question is telling me to draw a dot and cross diagram for a molecule of water, to state how many lone pairs it has, and to explain why water molecules form on average 2 hydrogen bonds per molecule, whereas the ammonia molecule forms only 1. So starting with the dot and cross diagram for a molecule of water, we have 2 hydrogen atoms and 1 oxygen atom. And so the hydrogens each share an electron with the oxygen. And so the oxygen shares an electron back. So they're 2 covalent bonds. And because oxygen is in group 6, that means it has 4 electrons which are left unbonded. And this is the dot and cross. And so for A, state how many lone pairs it has. That means it has 2 lone pairs. It has this one and this one. So these are lone pairs. And so it has 2 lone pairs. For B, explain why water molecules form on average 2 hydrogen bonds per molecule, whereas the ammonia molecule forms only 1. So if we have a look at ammonia, we have nitrogen, which is in group 5. So it has 5 electrons. If we bond 3 hydrogens, and these are all covalent bonds, then we have only 1 lone pair left, this one. And for hydrogen bonds to occur, we have to have a hydrogen and a very electronegative element. such as oxygen, fluorine, or nitrogen. So in both of these cases, they can both form hydrogen bonds. But with water, water has 2 lone pairs. So on average, it can form 2 hydrogen bonds because this one here can form a hydrogen bond with a hydrogen. And this one can also form a hydrogen bond with a hydrogen. Whereas with the ammonia molecule, it can only form one because it only has 1 lone pair. So it'd only have one going off in this direction. With a hydrogen, that would be 180 degrees, and these would all be 180 degrees. And that's why it only forms one, because it has 1 lone pair, compared to water, which has 2 lone pairs, so it can form 2 bonds with hydrogens. So before we start on number 2, feel free to pause on the video and try it yourself first. So ammonia is very soluble in water. State the strongest type of intermolecular force between 1 molecule of ammonia and 1 molecule of water. Draw a diagram to show how 1 molecule of ammonia is attracted to 1 molecule of water, including partial charges and all lone pairs. And phosphine has a structure similar to ammonia in terms of intermolecular forces, suggests the main reason why phosphine is almost insoluble in water. So first we're going to draw out the 2 molecules we have. So we have an ammonia, and that's NH3. So it'll look like this. With the 2 lone pairs. And then we have 1 molecule of water. So the water looks like this. And now we have a look at the intermolecular forces. So the 3 intermolecular forces are either van der Waals, dipole-dipole, or hydrogen bonding. And so, do we have van der Waals forces? Yes, we do, because they are present between all molecules. So we have van der Waals. Do we have permanent dipole-dipole? Yes, we do, because if we bond either the hydrogens with the nitrogen or the oxygens with the nitrogen, one of them will always be partially positive and the other one will be partially negative. So if we bonded a hydrogen to a nitrogen, there would be a permanent dipole-dipole because nitrogen is a lot more electronegative than hydrogen. So we'd also have that. But do we have hydrogen bonding? And now we think about hydrogen bonding, and we know that it occurs when hydrogen bonds with a very, very electronegative atom. So basically, it's a very special case of permanent dipole-dipole attraction. And it only forms between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. So because we have a nitrogen here and hydrogens on the water, that means that we do get hydrogen bonding, because if we bond a hydrogen to the nitrogen, that will form a hydrogen bond because of how big the gap in electronegativity is, because nitrogen is so much more electronegative. So the strongest type of intermolecular force between one molecule of ammonia and 1 molecule of water would be hydrogen bonding. So for B, draw a diagram to show how 1 molecule of ammonia is attracted to a molecule of water. So if I draw out the water first, it looks like this, with the 2 lone pairs on the oxygen. So the oxygen is much more electronegative, so we give that the delta negative charge, and the 2 hydrogens have delta positive charges. And then we have the ammonia, which has 1 lone pair on the nitrogen. Then we have hydrogen bonding between the oxygen and the hydrogen, because the oxygen is much more electronegative than the hydrogen, because the nitrogen would have the partially negative charge, whilst the hydrogens would have the partially positive charges. And this would be 180 degrees. So this is how one molecule of water would be attracted to one molecule of ammonia. So that's for B. So for C, phosphine has a structure similar to ammonia in terms of intermolecular forces, suggests the main reason why phosphine is almost insoluble in water. So with ammonia, the lone pair on the nitrogen can form hydrogen bonds with the hydrogen of water. And so hydrogen bonds form, which makes it soluble. But when we have phosphine, so we have a lone pair on the phosphorus, and then the 3 hydrogens. So this would be the partially negative. These would be the partially positives. Because the lone pair is on the phosphorus, this doesn't hydrogen bond with any of the water molecule, so that's why it's insoluble.